All right, let's dive right into this explainer. Today, we're decoding the blueprints of a hyper-advanced, mathematically perfect computing machine. And you might be wondering, why go to all this trouble? Well, because we are looking at a system designed to make traditional software bugs and crashes literally impossible. Imagine a world where standard programming logic is just gone, entirely replaced by pure, infallible geometric shapes. That is the tangent lambda Polytope model.
Now, to really wrap our heads around this system, we've got to appreciate the tone here. It's intense, right? This isn't just a friendly style guide or a polite suggestion for writing code. It is an uncompromising, automated developer mandate. It speaks with absolute authority, boldly declaring that the core layout is mathematically closed. Basically, there is absolutely no room for creative interpretation here.
So here is our roadmap for exploring this digital fortress. We're going to hit the automated developer mandate, the base geometric substrate, the 4 polyhedral jurisdictions, the blackboard field, formal cock verification, and finally, branchless execution. Let's get into it.
Section 1. The Automated Developer Mandate, or Isolated Repo Sovereignty. This is where the absolute laws of this computing universe get established.
The crucial takeaway here is that these constraints, they act as literal laws of physics for this system. The model enforces repo sovereignty. Think of it as a completely sealed-off island. It has to operate entirely inside its own context, and it is strictly forbidden from pulling in external frameworks or connecting to global networks. Even the file structure is locked down. That hidden .omd directory has to remain completely flat with exactly 23 assets. And get this, absolute zero internal subfolder nesting is permitted. None. It mandates a completely isolated self-hosting entity that relies purely on local standalone verification. Moving to Section 2. The base geometric substrate, the center of the universe. If that mandate is the law, well, this substrate is the physical ground it stands on.
Okay, so everything starts right here. Hex 0, 0, 0 degrees, the amino centroid. It's kind of like the absolute 0, 0 center point on a giant piece of graph paper. It's the definitive origin and pinch point from which every single spatial distance calculation and transformation is branchlessly derived. There's no relative positioning going on. Everything knows exactly where it is because it calculates its distance from this exact unchanging origin point.
And radiating out from that centroid, all coordinate claims are strictly bounded to specific local incident surfaces. They're all based on this magic number, 4,320. It forms a mathematically perfect grid expanding outward, kind of like perfectly spaced ripples in a pond, guaranteeing that every coordinate is known. The geometry scales up predictably across these surfaces. 4,320, its square, and its 4th power horizon. To keep all this math beautifully closed, the system uses a digital lock. Every single transformation calculates against this exact 64-bit constant, the Metatron pre-closure signature. Think of it like an unbreakable wax seal that's natively enforced right in the register blocks during every single state transition. It guarantees that the geometry stays totally intact and completely predictable without ever drifting off course.
Section 3. 4 polyhedral jurisdictions, physical zones of a digital world. So we've got the center, and we've got the grid. But how is this space actually organized?
It's honestly brilliant how they organize data here. Forget messy folders or abstract memory allocations. Data lives inside specific geometric shapes. User space? That's a tangent tetrahedron with a mathematical norm of 0. Local space is a regular tetrahedron at norm 1. Remote space is stellated at norm 2, and net space is triachus at norm 4. The various operational spaces, from simple local user graphs all the way up to vast net hypergraphs, are literally locked into these strict integer norms.
All right, Section 4. The blackboard field, the surface of visibility. Let's see how data actually interacts within this geometric universe. To really grasp the blackboard, you kind of have to unlearn traditional computing. The sources make it crystal clear. This is absolutely not a globally materialized database. It is not your standard shared memory. Instead, it's a bounded projective field. Think of it as a literal projector screen where independent, autonomous blocks of data can shine their light to be seen together, but without ever blending their source codes or giving up their individual identities. And sticking with that theme of super strict boundaries, this field isn't infinite. No way. It is strictly bounded to exactly 256 positions on a byte plane. Having this finite space completely prevents the runaway memory consumption you normally see in traditional software.
So, you might be wondering, how does a 256-position field coordinate everything? Well, it uses a mirror projection. Independent context blocks are placed on this board, and the field is split perfectly in half using just the 7th bit. From hex 00 to 7F is local, 80 to FF is remote. It's essentially an antipodal mirror, like perfectly folding the board in half. And an operation called tangent cons steps in to act as the traffic cop, letting these blocks coordinate visually while keeping complete ownership of their own data.
But what happens when things clash, right? If two pieces of data conflict, the system doesn't just crash or throw some random exception on your screen. Instead, it routes that overlap geometrically into what's called the residual field. It literally takes the traditional concept of standard error, STDER, and gives it a concrete spatial location. In this system, conflict is just another shape on the board.
Which brings us to Section 5, Formal Mathematical Cock Verification. Absolute proof. You're probably wondering how they can be absolutely sure this crazy architecture actually works.
The answer? An exhaustively strict mathematical proof process using the Cock Proof Assistant. They sequentially map every single bitwise token and structural constraint to ensure the source code perfectly matches verified mathematical proofs. They run a target called Make Proof Strict. It's like a math teacher demanding you show every single step of your work, and you have to pass with absolutely zero open axioms or assumptions. It mathematically proves that the code cannot do anything other than what the geometry dictates.
Just listen to this mandate for a second. Do not introduce software looping constructs or state mutators. Think about that. No loops, no while loops, no dynamic mutators, nothing speculative. Just pure, constructive geometry unfolding step by step.
And finally, Section 6, branchless, constant time execution. This is the holy grail of all these rigid laws and proofs.
Because of those hardcore proofs, the flat layouts, and the total lack of loops, every single state transition in this entire model resolves in absolute O of 1 constant time, meaning no matter how complex the system gets, every single action takes the exact same predictable split second to execute.
There are absolutely zero execution loops allowed here. The engine evaluates algebraic derivations straight onto the hardware registers. Everything is strictly bounded to a 64-bit register context and masked down to a 16-bit word footprint. The processing is instant and infallible. There's no branching logic to get stuck in and no infinite loops to crash your computer. It just calculates its next position relative to that ominous centroid we talked about, and it instantly moves.
Which leaves us with a huge question to chew on. We're so used to these sprawling, complex software systems with endless dependencies and totally unpredictable states. But if pure geometry can flawlessly dictate computation without a single loop or even a connection to a global network, what does this mean for the future of hypersecure systems? It really makes you wonder just how far we can push the boundaries of technology when we completely replace fragile programming with mathematically flawless geometric blueprints.